Chapter 8 is oversampling distribution, and in this section we are going to describe the distribution of the sample mean. And remember, sample mean is x bar. See if I can get this pen to work. And then we're going to describe the distribution of the sample mean. So distribution is just the shape. Whenever you see the word distribution, just think shape. And we're going to use x bar to approximate mu. So we're going to use the sample to approximate the mean. Couple vocab words. Sampling error is the error resulting from using a sample to estimate a population characteristic. And then sampling distribution, again, distribution just means the shape. So remember, x bar is a variable. Well, up until now, we've really been just talking about x. And so we're going to be focusing on the variable x bar. And so we're going to be looking at average, right? Because x bar is sample mean. Since all the variable, sorry, this is kind of formatted weird. My x bar is formatting weird. Since all variable have distributions, x bar, that should be over there, is also a distribution. And then we're going to talk about why x bar can be described as a variable now instead of just x. So for a variable x and a given sample size, the distribution of the variable x bar is called the sampling distribution of the mean. And so basically we're going to, again, just be using x bar to try to figure out what we know about the sample mean and what we can kind of conclude about the sample population. That slide repeated itself, sorry about that. Okay, so let's say we have 5 starters on a basketball team that have the following heights: 80, 78, 84, 73, and 84. Calculate the population mean for these data. So this is all of the people on the basketball team. And so if this is all, then this can be considered our population. And to figure out our population, we need to add them all together. So plus, 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 and divide by however many there are, which is 5. And that would give us our mean. And so when I do that, I get 79.8 inches. Make sure, if you need to, that you're doing this as well. This says, let's call this A. B says, make a table listing all possible samples of size 2 along with their sample means. Okay, so basically, I'm going to erase this real quick. All possible samples. So basically, I'm going to put every height with every other height with sample size 2 and figure out those means. And so I guess I'm going to do this in green because it's going to get kind of messy. But anyways, here, let's do it over here actually. Sorry. Here's my height. And then my sample mean. So I'm going to take each height. So for example, 80. And 80 needs to go with each one. So 80 needs to go with 78. And then another sample could be 80 and 84. 80 and 73. 80 and 84, right? And then I'm going to do this with the next one. So 78 needs to be with each of them. So 78's already been with 80. 78, 84, 78, 73, 78, 84. And I'm already running out of room, so I'm going to make another, keep it going. Okay, 84 needs to go. So 84, 73, 84, 84, 73, 84. So those last two need to go together. Okay, then I am going to average all of these together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 4, 6, 8, 10. Okay, so I'm going to average these samples together. And so let's go back to 80 and 78 right here. If I add them together and divide by 2, because there's 2 of them, I'd get 79. And then 80 and 84, average those together, 82. And I'm going to keep going until I get all the way down. So 80 and 73, average those, 76.5. 82, 81, 78, and 73 is 78.5. 78, 84, 78.5. Oh, wait. 81. Sorry, my notes are a little off. Let's see what I got here. 78 and 873. Let's see what that is. One second. Let me get my calculator out. Just make sure. Divide by 2. That should be 75.5. And then 78 and 84 is 81. That one's already up there. Okay, so I have a table of all the sample sizes of size 2. So like we randomly picked 2. That's what we get. Determine the probability. I'm on this one. Sorry, I don't have much room. That a sample mean equals the population mean. So remember our population mean, when we averaged these 5 together, was 79.8. Okay. And so I look down and I'm looking at each one of these and I'm trying to figure out if any of them equal 79.8. And they don't. And so the probability that they equal the population is 0%. Then it says determine the probability that a sample mean is within 1 inch of the population mean. So between 1 inch would be basically plus or minus an inch. So we want to know the probability it's somewhere between 78.8 and 80.8. So I'm going to circle all of those. Let's see. Go down my list. I see 1. Okay. So how many possible choices are there? 10. So 1 out of 10 would be 10% or 0.1. All right. So that is the probability that it would be within 1 inch of the actual mean. So we're going to repeat this with sample size 4. And I am just going to do a couple and then I'll just give you the value. So remember our inches were 80, 78, 84, 73, 84. And so here's our heights. And then it's a sample because we're only taking 4. We're not taking all 5. And so I should have left more room, of course, but I didn't. 80, 78, 84, 73, right? We're leaving out 84. And then maybe we leave out 73. So 80, 78, 84, 84. Okay, then maybe we leave out one of the 84s. So the third one. 80, 73, 78, 73, 84. So we keep going through this. Well, whoops. Let me just go ahead and write them all out. Then let's say we leave out 78. Okay. Then let's say we leave out 80. So let's average those together for each one. And so if I do that, I'm dividing by 4 now, adding them all up, dividing by 4. I get 78.75, 81.5, 78.75, 80.25, 79.75. So let's ask the same questions. What's the probability that we get exactly the mean? The mean is equal to 79.8. And so we don't actually exactly get the mean. So that's 0%. But what's the possibility, what's the probability that I get within an inch of the mean? So remember that was between 78.8 and 80.8. Well, if I go through, this one falls within, and so does this one. And 2 almost fall within. And so that would be 2/5 or 40%. That's pretty good. So the larger the sample size, it looks like, the closer we get to the actual mean. So we just proved it with a somewhat simple example with a small population size, only 5 basketball players on the whole team, right? But still, the larger the sample size, the closer we get to the mean. So that is the effect of a sample size. Larger sample size is better always. The possible sample mean cluster more closely around the population mean as the sample size increases. Very important. Thus, the larger the sample size, the smaller the sampling error tends to be in estimating a population mean, X bar by a sample mean. So basically, the bigger your sample size, the closer you get to the actual population mean. Sampling distribution, remember, all that means is the shape. The sampling distribution of a statistic is a probability distribution for all possible values of a statistic computed from a sample size n. The sampling distribution of the sample mean, X bar, is the probability distribution of all possible values of a random variable, X bar, computed from a sample of size n from a population with mean, mu, and standard deviation, sigma. Sampling distribution of the sample mean normal population. The weight of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. Approximate the sampling distribution of the sample mean by obtaining 200 random samples of size n equals 5 from this population. We're basically getting 200 groups of 5. So the data on the following slide represents the sample mean for all 200 random samples of size n equals 5. Let's just say that I'm not going to put 200 on here. Well, actually I am on the next 2 slides, but let's just say I picked 5 pennies and averaged them together and I got this. And then I did it again and I got this. And then I picked 5 more pennies and averaged their size. And then again and again, right? These are all X bars. They all represent X bars. And then if I average all of these together, I get a new X bar. So I'm basically taking an average of an average. So let's say I have all of these values. This is me picking 5 pennies and averaging them together and all the random averages that I get, right? And here's more averages, right? There's just a lot going on. And let's say that I add all these 200 averages together. So add together, and then I'm going to divide by 200. This is basically the mean of the mean, right? I'm first taking a mean, and then I'm taking another mean. If I added all of those 200 sample means together, I'd get 2.46, the same as the mean of the population. So in doing this, you will either get really, really close or you will get the same mean as the population. So it's a really good estimator. And then the standard deviation was 0.0086, which was actually smaller than the standard deviation of the population. And so here on this next slide, we'll show the histogram of the sample mean. I apologize. I don't know why this is cutting off, but use your imagination that it is actually going to be normally distributed when and if we were to create a histogram of these data. So again, use your imagination. We've got something here that looks normally distributed, and so let's say this time we take a sample size of 20. And when we take a sample size of 20, we get 2.46, but our standard deviation is now 0.0045. And so it's a little less. And so then when we did n equals 5. And so that's the goal. There's less variability in the distribution, and we want less variability. Because of that reasoning, you can get, when you do basically the mean of the mean, you can get very, very, very close to the actual mean. And so whenever you find the mean, that's just going to be your mean. But because standard deviation still has a little variability, and the bigger the sample size, the closer we'll get, to find the samples, to find the standard deviation of what we're going to be doing, we'll actually need to be using this formula. And so do go ahead and look at the notation. It looks like the mean of X bar, mean of the mean, is still just equal to the mean because we can get really close. But the standard deviation of X bar basically is equal to the standard deviation divided by the square root of n. And that's just because we're trying to take into consideration the variability that's going to take place. The shape of a sampling distribution, if it's normally distributed, then the sample mean will also be normally distributed. And so here's what we're used to. When we're doing x, we're used to z is equal to x minus mu divided by the standard deviation. But what about when we find a z for what we're talking about now? Well, x is now going to be x bar. Mean is now going to be mean of x bar. And standard deviation is now going to be sigma divided by root n. Well, remember we said earlier that the mean is just equal to mu. So really we can erase that if you really want to. And so really the only thing that's changing is the standard deviation. Now you're going to be dividing by the square root of n to take into consideration, again, that variability. And if you put this in your calculator, I'd do the top divided by the bottom and keep the top, the numerator in parentheses, and the denominator in parentheses as well. So let's do an example. Determine, so the weight of pennies minted after 1982 are approximately normally distributed. Remember, that means that you're basically good to go to use your Z. with a mean of 2.46 and a standard deviation of 0.02. So it's going to, 9 times out of 10, it's going to give you that information. It says determine the mean and standard deviation of the sample mean for sample size 10. Now remember, the mean is just the mean. So what is our mean? 2.46. Done. But remember, the standard deviation is whatever standard deviation they're giving you divided by root n. And so we were given 0.02. What is our sample size? 10. That's what n means, sample size. When I put that in my calculator, I get 0.0063. Okay? So, that's that first part. I'm going to go ahead and erase that and then put that back on A. Okay, so mean. And then standard deviation. Oops, sorry. 0.0063. B says, what is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least? So we're doing a z-score with this information. Okay, remember z is equal to x bar minus mu of x divided by standard deviation. And we want to find at least, so at least 2.465 at least means more than. So I'm going to input this information, 2.465 minus 2.46. So we're just doing a z-score with this new information, with the mean of the mean. And that's all we're doing. And I get 0.79. Remember, at this point, you need to look this up in your z-score chart. And when I look this up in my z-score, I get 0.7852. This is the same thing as 0.79. So look up 0.79 in that z. Now this 0.7852 represents the area to the left. We want area to the right, right? At least. And so to find area to the right, I need to do 1 minus that 0.7852. And I get 0.2148. And that's the probability that my x bar, my sample mean, is at least 2.465. So what happens if my distribution is not normal, meaning it doesn't create that symmetric histogram? An example of that is rolling a fair die, right? That's going to give me a uniform distribution because they all have the same outcome of happening. So if they're not normal, estimating the sample distribution x bar by obtaining 200 simple random samples of size n equals 4 and calculating the sample mean for each 200 samples. So if we were to repeat that again for a sample size of 10 and 30, you can see the histograms. 1 second. So that's n equals 4, n equals 10, and n equals 30. Pretend that looks like that. This did not get down for some reason. So anyways, some key facts are as your sample size n increases, we will get more normally approximated, so we'll get more bell-shaped. And then the mean of the sampling distribution is equal to the mean of the population. And then the samples, the standard deviation will always be this sigma divided by root n, regardless of your sample size, because there will still always be some sort of variability. However, it is hard to say, well, what is a good sample size and what is not a good sample size? We know as the sample size gets bigger, it becomes more normally distributed. But we're going to have, if you will, a rule of thumb. We need to at least have this, and that sample size that we need to at least have is 30. It needs to be at least 30. That was not a good 0. It's kind of our rule of thumb. It's because we don't want to draw a histogram every single time to make sure we're normally distributed. And sometimes it could tell you we're approximately normal or we're normally distributed. And if that's the case, if it says that, then you're good to go. But if it doesn't say that, you need to check every time. Is my sample size at least 30? Yes. Okay, we're good. Okay, so this says, suppose the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2. It says, if a random sample of n equals 35 oil changes is selected, describe the sampling distribution. So describe the shape. Well, nowhere on here does it say that it's normally distributed. Doesn't say normal. Well, how do I know? Well, I can use my new rule. Is n at least greater than or equal to 30? My n is 35. Is n greater than or equal to 30? Yes. If this rule is in place and it checks out, you can say it's normally distributed or bell-shaped or whatever. Remember, those words pretty much all mean the same thing. If you can say it's normal, if you can say it's bell-shaped, then you can find the probability. Then you can use those z scores. So, if a random sample is selected of n equals 35, what's the probability that the mean time is less than 11 minutes? So this is our x bar. So we're going to use that same formula as earlier. X bar minus mean divided by standard deviation, which is now sigma divided by root n. My x bar is 11. My mean up here was 11.4 divided by, my standard deviation is 3.2 divided by the square root of 35. Remember to keep top together divided by bottom together. If I put that in my calculator, I will get negative 0.74. And I want less than. So I'll look that up in my Z chart and I get 0.2296. And we need to think about what this means. This is area to the left. And we wanted less, so this is my answer. I'm about to erase this. So if you need to write it down, go ahead and pause the video. Okay. C says if a random sample of 12 oil changes is selected, what can be said about the sample mean? Well, n is 12. And let's look at my rule of thumb. N needs to be greater than or equal to 30. Is 12 greater than or equal to 30? No. So we don't know the shape. Unless we look at the data and create a histogram ourselves. But based solely upon this rule, we can't comment on the shape because it doesn't meet that requirement. 8.2 is very similar to 8.1, except a big distinct difference. We are now talking about proportions. And this is going to be kind of the formatting for the rest of the semester. The first section will be talking about mean, and the second section will be talking about proportion. We're going to be doing a similar situation. We're going to be talking about sample proportions. Proportions can be percentages, fractions, decimals. Those are basically the three main types of proportions. And so a point estimate is simply something that estimates a population. And so our point estimate is going to be denoted by a p hat. And that p hat looks like this. It looks like a p with a hat on it. And it's going to be some x divided by n. Like I had 20 out of 100 dogs. I don't know. In my house. That would be a lot. But that 20 would be the x. The n is the whole. So part over whole. And then p hat estimates the proportion, which is p. So p hat estimates p, just like our x bar estimated our mu. Okay, so this poll conducted that 1,745 registered voters were asked whether they approved of the way George Bush is handling the economy. 349 responded yes. Obtain a point estimate for the proportion. So point estimate for proportion, we know right away we're going to be doing p hat because that's the proportion of registered voters who approved the way that George Bush is handling the economy. So how many total people were asked? That 1,745. And then how many people approved that or said that he was handling the economy well? 349. If I were to put that in my calculator and get a decimal, I'd get 0.2. So that's your p hat. P hat is equal to 0.2. So it's always part over whole. Once again, I have no clue why these are not showing up. But it's basically saying, that wasn't very well, that the more sampling distributions, the more samples you do, the more normal it gets. If you want to look at this on your slides, on your blank slides online, then that's completely fine because I apologize. But basically, this one looks like this. Maybe this one looks like this. And then this one's almost perfect. So it's the same story as the mean. As the sample size increases, then it gets more normal. So there's a couple things that definitely help us figure out if our data is approximately normal. And so we can look at the shape, center, and spread. And obviously we know that as sample size increases, we can become more approximately normal. The mean of the sampling distribution equals the population proportion, should be in the center. And then the standard deviation will decrease as the sample size increases because it becomes more normal. So, you've got different rules depending on if it's a mean or a proportion. And so we're talking about proportions right now. And to find, just like with mean, we said it needs to be at least 30. You need to do the same thing with p hat. But to find if it's normal, you do n times p times 1 minus p. And that value needs to be at least 10 or equal to 10. Once again, the mean is what it is. You don't have to do anything else with that. But the standard deviation formula is a little more scary. It's the square root of p times 1 minus p divided by n. And so we're going to kind of talk about that on the next slide. So once again, you want at least the sample size to be no more than 5% of the population. To be honest, I don't worry too terribly much about this rule, but I do want you to always check that n times p times 1 minus p is at least 10. And then if it's not, it means it's not normally distributed. And then once again, this is the standard deviation formula. You are not given this, but you are given this on your formula sheet. According to a time poll conducted in June 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. Suppose we obtain a simple random sample of 50 voters and determine which voters believe that gay and lesbian couples should be allowed to marry. So we want to find the sampling distribution. And to find the sampling distribution, we basically need to see if it passes this rule. So first we need to figure out what is our N. How many people did we ask? We asked 50 people. Sometimes you have to find your p hat. Or your P, depending on which one you're given. And sometimes it's just given to you. And in this case, we were given a proportion of 42%, right? Proportions are percentages, decimals, or fractions. And I'm going to turn this into a decimal. So my P hat is 0.42. And so I'm going to use this formula. So N times P times 1 minus p needs to be greater than or equal to 10. And I actually get 12.18, which is greater than or equal to 10. And we can say that we've got a normal distribution if we pass this rule. Okay, according to the Center for Disease Control, 18.8% of school-age children 6 to 11 were overweight. In a random sample of 90 school-age children 6 to 11 years old, what's the probability that at least 19 are overweight? And so we're going to be doing a Z again. And first off, a Z for proportion is sample minus whole divided by standard deviation. And that standard deviation for proportion is that big P times 1 minus P divided by N. So we're going to be using that. Now, before we use that, we have to figure out if this is normally distributed. Use that rule that we just used. And so my N is 90. So 90 times my P, which is 18.8, times 1 minus P, needs to be greater than or equal to 10, and I get 13.7, so I'm good to go. This is normal. So it says, what's the probability that at least 19% are overweight? So that's my P hat. That's like what I'm looking at specifically. And so 0.19 minus my P, what I know about everybody, divided by the square root of. P is 0.188. 1 minus 0.188 divided by N. 90. This gets real tricky in your calculator. You've got to be really careful about the denominator, keeping all that together. When I put this in my calculator, I get 0.005. So it wants to know the probability at least 19% are overweight. This value that I just got is my z-score. When I look this value up in my z-chart, I'm about to erase this because I'm running out of room, so if you need it, write it down, pause the video. So Z is equal to 0.05. The probability that goes with that is 0.5199. But we want at least, so at least means to the right, And so that 0.5199 gives me the area to the left. So I need to subtract it from 1 to get the actual value, 0.4801. Okay, so 4801. The last question asks, suppose a random sample of 90 school-aged children from 6 to 11 results in 24 overweight children. What might you conclude? So let's figure out what our p-hat is. It doesn't give it to us. It said 24 out of these 90 kids were overweight. So that's 0.2667. What might I conclude? Well, it said that the whole population, 18.8% of school-age children were overweight. That's a really high number from that 18.8%. And so it really doesn't represent the population well, because the population is a lot smaller than that. So that is what I might conclude, that maybe we just happen to get a lot of overweight children in that sample.